Good evening, dear colleagues. I have a pleasure to introduce our today's speaker, Hovhannes Khudaverdian, who will speak about odd symplectic geometry and Batalin-Vilkovitsky formalism. So you're welcome.
Yes, thank you very much. Okay, I just would like to write again title of the talk because everything is all right. Odd symplectic geometry in BV-formalism. And I would like to add odd symplectic geometry in BV-formalism and half-density. So the title of my talk will be odd symplectic geometry in BV-formalism. And half-density. Okay. Now, it's okay to speak in this way. I need to swap it. Now, there are two, in supermathematics, there are two versions, exactly two versions of symplectic geometry. So, usual symplectic geometry, it is when we have closed differential form, which is degenerate. And this closed differential form defines symplectic structure. So in the super case, we have even symplectic geometry and odd symplectic geometry. So let's consider two cases. First case, even case. Dimension m equals 2pq. In the vicinity of arbitrary points, there are local coordinates x, I, theta, alpha, such that in this coordinate, it is something like Darboux theorem, but weak version of Darboux theorem. In the vicinity of this point, there is a coordinate x, I, theta, alpha, such that to form which defines symplectic structure, it is dxi, where dxi plus p plus epsilon alpha d theta alpha. Of course, I will not use today odd form, but I will write just formula for. Of course, we can write Poisson bracket. It is Poisson bracket corresponding to even symplectic structure. It is the degenerate Poisson bracket at G.
I don't understand the second sound.
It is epsilon alpha plus epsilon alpha takes 1 plus minus 1.
And yes,
Epsilon alpha square.
and d square.
Yes, square. Let me write Poisson bracket, maybe it will be much better. Because df dxi dg dxi plus p minus dg dxi plus p df dxi plus here I forget I think it was epsilon alpha df d theta alpha d theta alpha dg d theta alpha. Yes. Okay. It is even structure. In the case if there is an odd structure,
Well, can you speak towards the microphone? Because when you turn to the board,
you see, when I go to blackboard, you don't listen to me.
You see, we have
when you turn your face to the board, the sound is not clear.
It's in a sense unsolvable problem because we use microphone of my computer, and when the speaker is far away from the computer, well, the sound we can do nothing. Technicians couldn't help us. The microphone doesn't work.
I will try.
So it's better to be nearby the computer.
I will try to be as close to computer as possible. Okay.
Just turn your head when you speak to the computer.
Yes, but I had. Okay, I didn't see one here blackboard, so okay. I will try. I understand. I will try.
Move a little bit the computer to the left, to the center of the board. It's David. Hello.
Он в центре находится. Компьютер находится. No, компьютер is.
Okay. Okay.
Okay, we try. Okay, we will do our best. Okay, we understand the problem. We'll do our best. So let's consider second case. Second case, it is when you have odd bracket. Because we don't need even bracket. Today I will not use even bracket. So I will remove all the stuff. Okay, no, let me. So in the case if we have odd bracket, if you have theta such that P of theta equals 1, the classification theorem, Darboux-Witt theorem, will say the following. If dimension m equals n, so number of even variables is equal to number of odd variables, then closed differential form, which will be non-degenerate in this case. There are Darboux coordinates, there are special local coordinates in the vicinity of every point such that form will be equal to dxi dθi. And one thing which I will use today very often, it is why it's very important. The corresponding bracket, non-degenerate bracket of two functions. If we have n supermanifold, we have xi, x even coordinates, theta odd coordinates, and odd bracket fg equals df dxi dg theta I plus, here I will be very careful because it is a sign df d theta I dg dxi. This bracket has many different names, and I will tell you from now, I will not speak about history, but this bracket it has, of course, we can call it naturally odd Poisson bracket, canonical odd Poisson bracket, odd Poisson bracket, canonical. We can call it quarter bracket, we call it Butin bracket. Butin, she was being the student of Colton, Butin bracket. And he insists at another name, which is very important. Physicists call this bracket anti-bracket. All these names have its reason, raison d'être. Okay. And today I will speak about this bracket very often. Now, we have this bracket. We have Darboux. Now, two words about generalized Darboux theorem, because, okay, I will speak only about odd bracket now. So I will remove all the stuff related with even bracket. Now, if you have symplectic structure, even or odd or usual, you have Darboux theorem. Darboux theorem, it's very important to know because it gives answer on many questions. And the formulation of Darboux theorem in the even and odd case will be the same with a little bit differences, which I will tell later. Now, so if you have arbitrary manifold M in odd symplectic superspace, and this manifold is non-degenerate. What it means non-degenerate? Non-degenerate means that if you put differential form, if you consider differential form on it which defines symplectic structure, it is non-degenerate. Then you can always find changing of coordinates such that xr equals, so you have congeneric surface. It means that M has dimension kk, and if M is dimension kk, you can always find coordinates adjusted to this surface. So it means that you can find coordinates such that xr equals 0 up to the order of x power p, where p is arbitrary number, and theta r equals 0 up to the order of. This theorem, to prove this theorem, you don't need. It is very technical theorem, but this theorem is very important to understand when you are trying to find invariance. In Darboux theorem says you that you can kill, if you have manifold, you can kill all the derivatives. It means that you cannot define. It is the reason why, for usual symplectic geometry, you can write only invariance in the first derivatives. Okay, I will not speak about these things, but what it is important for me today, that for odd geometry, there is no something like Liouville theorem. Let's remember that in usual symplectic geometry, we have keeping close to form. If you have close to form, you can consider its wedge product. So you can consider volume form for this. It means that usual symplectic geometry preserves volume form. In the case of odd bracket, there is a very interesting phenomenon. While odd bracket was considered very exotic object from the beginning, that if you consider, for example, let's consider double coordinates, x1, θ1, x2, θ2. If you consider, for example, x goes to 3 times x, and theta goes to theta divided by 3, it will be transformation which does not change symplectic structure, but Berezinian of this transformation equals 9. So we see that in the case of odd symplectic geometry, you have to care about volume form too. There is an exact theorem, it can be proven, but I will not speak about this theorem, that there is no any volume form which is preserved by symplectic, by odd transformations. It means that if you want to consider some constructions which we will speak about today, you have always to speak about symplectic transformations preserving some volume form. It is very important remark which I wanted to do. The second remark is that now let us see what's happening in 70s. In 70s, and Berezin and latest understood very well that there is even odd symplectic geometry. But even odd symplectic geometry was considered as an exotic counterpart of usual one. People was not considered that it is very important before 1981. In 1981, it appeared seminal paper of Batalin and Zirkovitsky, where the name of the article, it was 5-6 pages, gauge field of quantization, where they suggested the way to quantize every theory in Lagrangian framework, not in Hamiltonian framework, but in Lagrangian framework. You see, the problem is that in the FIAN, people were considering, okay, in the FIAN, in many places, people were considering quantization of arbitrary theory in Hamiltonian way and in Lagrangian theory. If you consider Hamiltonian way, it is the time to speak now about it, but if you have Hamiltonian formulation, one of the ways to consider Hamiltonian formulation, it is called to BV-formalism, but on the level of the formula, people use even symplectic geometry. And the most surprising thing, most shocking thing of Batalin-Delkovitsky formalism was that to define the structure, they considered odd symplectic geometry. Let me tell you about receipts that they gave. They consider arbitrary theory. Of course, here I have to tell very shortly about, in fact, what's happening in 70s. This theory began in 70s. People tried in 60s. In 60s, it was very famous work of Fadeev Popov when they did quantization of gauge fields. And to make quantization of gauge fields, they considered it was people already were used this terminology, this physics intuition, that you have to consider space of ghosts, anti-ghosts. And for example, to define Fadeev and Popov, when in 1967 they defined how to quantize gauge field. They defined technically, okay, I wouldn't speak about it, but technically they considered some functional, non-local functional. And to make this non-local functional, which was proportional to determinant B, they considered anti-commutic variables because they need determinant they need to express determinant B. Some people are telling here, I want to tell you that some people, sometimes I'm listening to the expression that, okay, it was burning of supersymmetry. It was nothing to do with supersymmetry. Okay, they considered odd variables, but soon as supersymmetry began, when you have mixing of variables, it is what Berezin was doing. Okay, I'm sorry for this reminder. Now, let's go on. Okay, so I promised to say two words about Batalin-Delkovitsky procedure. Batalin-Delkovitsky procedure, they deal with Lagrangian, with arbitrary Lagrangian. Of course, if you have arbitrary Lagrangian, the problems began if you have valet of the stationary point. So if you have Gaussian Lagrangian, which is degenerate, DQI, DQD, which is degenerate. It means that you have valet of stationary points, and it is something. Batalin, they consider arbitrary Lagrangian, which depends on the field, on the derivatives defined. Then the receipt, I think that today I will give you some ideas of why they came to the receipt, in spite of the fact it will be a little bit complicated, but okay, I will try, maybe. But now I will write this receipt only formally. So they consider master action. So they considered master action S, which depends. Okay, now I will write something. Here you have fields, which depends on fields and anti-fields. I will try to explain what is it. What is fields? Fields of the theory. It is usual fields Fi, but you have to consider both because you have to consider some surface gauge surface and some integration something like both. The crucial idea of Batalin-Delkovitsky was the following. They say that if we want to quantize the theory, we have to consider anti-fields which have opposite parity. If field is even, anti-field is odd, and so on. Is bound. And in the space of fields and anti-fields, they defined Poisson bracket. I will write this Poisson bracket because I want to tell you two words about my main topic, what I will speak about today, will be about fine and odd symplectic geometry. But yes, the space is double. Yes, yes, space is double. Space is double. And let me write FG Poisson bracket. It is df by dci, dg by dci plus something for fun, df dci. We will write in the same way like this Poisson bracket, but in the infinite space, plus df by dc star A, dg star A. And this has to be integrated over the it is okay, it's much better to look here for Poisson bracket. Today, I will make this comment. I want to make the comment. Of course, all the constructions which I will speak today, I will speak about finite dimensional odd symplectic geometry. People, the reason, there is a very important reason you have to understand that in Hamiltonian language, okay, people speak about even geometry, but in Hamiltonian language, you always can consider toy examples of Hamiltonian, for example, with 2 degrees of freedom and something like this. And at the end of the day, you will come to finite dimensional problem. If you want to speak about odd bracket, people always ask, can you consider odd bracket in 2-dimensional space, in 3-dimensional space? I'm sorry, from very beginning, odd bracket means infinite dimensional space, space of the trajectory. This is a problem. It is a problem. Why? Because next operator, which I will write, of course, there is a Poisson bracket, which I wrote here, almost I wrote here. And the second object, which was very crucial, I still didn't write master equation of what happened. Look at this here. Second object that they wrote. We have action, then we have a master action. Master action, which depends on the field. But usually the action depends on the class. No, action depends on the fields. Depends on the fields. Okay, part of the field. Okay, part it is field. Yeah, it's okay. No, it's okay. The problem is that master action, which depends on fields, is star. It obeys to the following equation. Master action, let me write master action. It is usual action S of y. Plus symmetries of this action are alpha. Let me write R alpha, C alpha, Y R star. Plus, okay, that in this master action, you will consider all the terms which are responsible for the gauge transformation, and this master action obeys to the equation odd Poisson bracket S equals 0. Okay, I can write. No. It is terms which are depending on the structure. For example, in this case, it is symmetry. Next term, it is related with commutator with all. And they are going down. It will be many things. Yes. Okay, I don't want, but all these terms are they can part in this equation as S equals 0. It is so-called classical master equation. Capital phi is
a collection of small phi's, yes?
You have phi A. It is fields,
Yeah.
it is ghosts, and so on. It is like random multipliers. And then you have P star A, which are anti-fields, or I star, which are ghosts, anti-ghosts, and so on. So you have collection of, so to define the theory, you need action. Using action, you solve this differential equation. In the solution of this differential equation, it will appear all the terms which are responsible for this term. Now I will come to the second and the most intriguing object of Batalin-Vilkovitsky formalism, which in classical physics, still people consider very okay. It is classical master equation, but how to write quantum master equation? Quantum master equation. Batalin-Vilkovitsky suggested new operator, and this operator I will write. Okay, of course, this operator. You remember this bracket, all this stuff that I wrote before it. You can write infinite dimensional space in infinite dimensional case. Unfortunately, the operator which I will write now, still people, for example, Tutin till now is saying that he does not believe that this operator has meaning. But okay, this operator which called Batalin-Vilkovitsky operator, it is derivative is square this is A. Okay, of course, from now on, I will go to the final dimensional symplectic geometry because I don't want to speak about.
Why is this operator any more controversial than the operator which appears in the Poisson bracket?
It was a bracket that is okay.
Why is this more controversial?
Because the second of the limited view.
I see. Because it's not invariant.
It is not invariant, it's okay. Okay, so let's consider final symplectic geometry. So from now on, we consider ENN. We consider coordinate, double coordinate xi, x1, and equal 1 to that. Our quantum bracket, which I wrote here, it will be xi, the j, equal to the ij, xi, j, with 0, and theta I, theta j, it's okay, there is no problem. The data operator, I will write it now. And it will be b squared xi theta I. It was, in some sense, yes. It is second. Of course, there's so many ways to criticize this operator. First of all, it is not invariant under transformation which preserve odd bracket. If you consider, okay, I will speak about this operator. But this operator, in fact, if you first question that you will ask, but before discussing, because today I will speak about this operator, about properties of this operator. Before speaking about it, let me distinguish between finite dimensional case and infinite dimensional case. I see, and it is a real problem, that many problems that I will discuss today, it will be about even symplectic geometry in finite dimensional case. But nevertheless, people, what they consider symplectic geometry, they consider in infinite dimensional case. And of course, many things are ill-defined here. But from very beginning, you have to understand it.
Is it possible to comment by Zoom? Does it work like that?
Okay, yes.
I just wanted to comment that the question is not so much about infinite dimensionality, but about locality.
Yes,
so
locality.
the problem is that delta is not defined for local functionals, But in principle, of course, in field theory, we are mostly trying to deal with local functionals. But if we allow non-local ones, it can be well defined. The problem is that in field theory,
you're absolutely right. It is, but I don't want to go in detail this question because yes, but yes, you are right. You are right. Yes, I agree with you that it is. Now let's continue about this operator. I just wanted to say that we have, first of all, we have this operator. Let's speak about this operator. Because this operator's first question that you asked me, what happens with this operator if you consider arbitrary canonical transformation? It's very interesting. Let's consider infinitesimal canonical. So we have operator which sounds very simple. The square, the exact. Let's consider the following result, which you almost will believe it's very good exercise, which you can do. Let's consider arbitrary infinitesimal canonical transformation induced because we have odd bracket. We have to consider odd Hamiltonian. So let's consider arbitrary Hamiltonian, which is odd. And let's consider arbitrary transformation xi goes to xi plus epsilon minus epsilon dq theta I and theta I goes to theta I plus epsilon dq dxi. Yes. So you can see, you take Hamiltonian vector field and see how this infinitesimal transformation, it is canonical infinitesimal transformation. If you do calculation, which is very beautiful, but I have the time to do, you will come to following result. The vector.
Wait, so Q is a function, odd function of arbitrary degree.
Yes.
Odd degree.
Yes. It is odd function which induces infinitesimal transformation, and we see what happens with this operator, second order operator. It is awful calculations if you don't understand geometry of this, but we can do it. The delta will be equal to delta if delta of Q equals zero. We come to following conclusion. So if Q is a function which is, for example, which is quadratic and which possesses properties Laplace Q equals 0, it induces infinitesimal transformations which preserve this operator. So from very beginning, the operator which wrote Batalin and Zilkovsky in 1981. Sorry?
You don't have epsilon squared and so on. It's just the first order calculation.
It's first order, but it is exactly. It's exactly. Okay, it's exactly. You can do this exact calculation. Later we did exact calculation. The problem is the following. Listen, there is another problem. You can ask me another question. What happens in you? What corresponds to this? Because usual symplectic geometry, we know everything, but never this operator appeared in usual symplectic geometry. What appeared? What is counterpart of this operator in usual symplectic geometry? Why it is so? So this operator is very strange operator. And the first question that people have to answer on, it is what's the geometrical reason? I will write this operator, but before it, I want to tell you that what happened in 80s, people didn't pay much attention on this method because all Lagrangians, which already they knew how to quantize, they quantize using another scheme of adding some components. And it is only after 1990, okay, it is.
Already tell us why we even have this operator.
I just want to tell you that, okay, I just tell historical. No, this operator looks very strange, but they wrote this work in 1981, and it was in 1988 when people wrote this operator. 7 years passed. But I will write the answer. Answer is very simple.
Why did they write it
No, indeed, I want to, okay, maybe, no, I just want to say the historical reason that 7 years, no, they wrote the method of quantizing anything. Sorry, I just want to say that this method people didn't use much. Okay, so first question that I want to answer, how to write this operator data in arbitrary? You remember, for odd bracket, I said at the beginning that you need volume 4. So if you have, so we consider now symplectic geometry. So we have symplectic space, and then you can see the post, and you have volume 4. And you remember I said that let's consider not only symplectic space, but because in symplectic space you can come to the transformation which do not preserve volume 4. In the case of odd geometry, you have to consider transformations which preserve some volume 4. So from geometrical point of view, we consider this structure. And let us, for this structure, consider the following operator, which sounds very simple. Let us consider for every function f, we consider Hamiltonian vector field of this function, and then consider divergence with respect of this volume 4 of this Hamiltonian vector field. So let's consider operator. Let's consider operator which equals 1 divided by 2. Okay, this coefficient. Divergence with respect to volume 4 of the Hamiltonian vector field. Let's recall what's the divergence of vector field. You see, you look how volume 4 is changing under the action of vector field. So here it's written 1 divided by 2 minus 1 power f, the derivative along the f of the volume form divided rho. And this was this operator. So my first statement is that this operator you can write very simple. Of course, when you wrote this operator, you are surprised. You say, but why people didn't spend much attention on it? I remember I was speaking with different, it was very interesting historical cases that many mathematicians, some mathematicians was telling me, okay, it was evident they didn't understand that. But okay, it is something that, so the first statement, you have to write this operator. And people were working 7 years when they wrote this operator. When you wrote this operator, let us write this operator in the way, you remember when I wrote master equation, I wrote in terms of delta 0. The first question that you will ask me, how this operator mimics this operator delta 0? It is very simple operator. Let's do the following exercise. It's very important, this exercise. How we have to choose volume 4 to come to this operator. The point is, let me tell you one thing. In the supermathematics, there is a conception of so-called coordinate volume form, x theta. I would say that volume form is coordinate volume form. Let's remember, I'm sorry to recall you, how you integrate function in supermathematics. If you have arbitrary function fx theta, and if you have coordinate volume form x theta, you have to take here the term which possesses maximum number of theta and just integrate it over x. Just integrate it, for example, this function, the expanded function. If we have f0x plus with the same term which possesses f I x equal 1, equal 2, equal n, and contribution to the integral, to the residue integral, which is the last term. It will be f I x with dn Now, no, I just write definition of Perez integral.
And how does the volume form and the final?
Here we go to, okay. Here we go to the, okay, you can write in this volume form. Here you go to the usual integral over dmx.
But what's the rule?
No, I just want to tell you that, okay, people sometimes, okay, let me write that there's a convention which I don't like, fx theta. People sometimes say dx1, dx2, dθ1, dθ2, yes? They say, it is my reason I want to explain that this notation is very bad notation. It is why I prefer to write instead this notation.
Yes.
I prefer to write this notation.
Yes, it is clear, but well, if you have an arbitrary volume form,
If you have arbitrary, I will write the function. Arbitrary volume form rho is a function of local coordinate.
we know that G is
D doesn't go, sorry. Here I know everything is okay. I define the integral. You have here, it is here integral here. What is the problem? I don't see. No. If you have, for example, line. For example, you have line. For example, you have line 1. Let's consider, for example, dx theta. Dx theta. If you have function, for example, if you have function fx theta, dx theta, you have to take this function f, which possesses to term fx plus theta times gx, and this integral equals integral gx dx. And here it is Bayesian rule, Bayesian integration.
So, but I don't understand then what is the role of G. So in the left hand side you have G, and
In the right hand side, okay, I don't argue. Okay, if in the right hand side, it is usual integration. It's usual integration.
yes, I understand. This I understand. I don't understand why do you need G? Right here instead of G something different, H, and the answer will be the same.
It's notation. It's notation.
But
No,
the few forms are different.
no.
Both the conventional volume form. D is like the canonical one, and then everyone else is related.
Coordinate volume form. I give definition of coordinate volume form. DA, it is coordinate volume form. It is coordinate
So
volume
the standard
Okay, listen, if you don't like it, I can.
D is not general here. D is very specific.
So what's the question? What's the question about the volume form?
it's a very just DX1, DX2.
Yes, it
It is exactly the thing which he doesn't like. Then everyone can understand, by the way.
Yeah, sorry. Yes. Yeah. Okay.
Oh, you don't like it because it's not invariant.
No, because it is very misleading. Because if you have, it's very misleading. Yes. Yes, we have integral. Yes. So if you have the volume form dx theta, rho. So the plus rho equals. It's very easy to see. If you have arbitrary function f, this arbitrary function generates Hamiltonian vector field fx I d e I plus f I d theta I is equal to f theta I with d theta I d by dx I plus f dx I d by dθ operator look in usual geometry? In usual geometry, unfortunately, I have maybe at the end I will speak about this operator. In usual geometry, it becomes first order differential operator. It is why we never noticed it, which is yes. The operator, if you in the usual geometry, if you consider operator delta f, which is equal to 1 divided by 2 divergence, Hamiltonian question. First of all, you say, listen, if you have divergence with respect to volume form, in the usual geometry, you have the volume form, so this operator equals 0. Of course, but you can say, let's consider arbitrary volume form. If you consider arbitrary volume form, you will come to the first order operator, which leads to the cohomology of Poisson geometry. But now I will speak about it maybe later. Maybe I just want to say you that this operator which I wrote. So two things I checked. That operator which I wrote in the case if rho is coordinate volume form is just operator delta 0. Let's write this operator. It's one thing. How this operator looks in the case let's write how this operator looks in the case of how to write master equation with this operator. For example, master equation which wrote Battalion, it was delta 0 E I S divided K. It is quantum master equation. The classical master equation, if you consider terms proportional to H, it will be S here master equation. Now, the second thing that I want to speak about, so the first thing that I introduced you now to understand the geometry of this programming, I introduce you delta operator. Let's consider some example of what's manifold. That depends on the volume form. No, if you consider, okay, let's see. If you consider delta for the xi d theta I of T I S H, the first term, it will be dxi, it will be r divided by h ts theta I. Then if you can collect the terms of the order h, then you take du by x of x, and you come to the. So the order h term is the same as this. It is quantum. It is what I say. It is quantum equation. If x goes to 0, it goes to the classical equation. It was classical equation, not quantum equation. Now let's consider example. I want to consider an example, basic example of odd-symplectic manifold. So odd-symplectic manifold. Odd-symplectic manifold. You know, in the usual symplectic geometry, there is a theorem which belongs to Weinstein constant that if you have every manifold, you have cotangent bundle has a structure of symplectic manifold. And in some sense, this example is basic, but up to some. There is a constant Weinstein theorem that if you have every Lagrangian surface, then in the tubular neighborhood of Lagrangian surface, cotangent bundle behaves as this cotangent bundle. In the odd symplectic mathematics, because you have no topology, as people like to say, there is a statement which I like very much, that every manifold, every manifold ENN is symplectomorphic to 50 star. This theorem can prove where M it is underlying manifold of E. So if you consider arbitrary supermanifold, you can prove the theorem, which I will not prove you, but it is a very beautiful theorem. So in some sense, all the examples are restricted by this case. Yes, it is global. It's one of the examples. You can prove. No, it's global statement. Global. It's global statement. It's global statement because no, it's global statement. It's global statement. I proved the global statement. It is global statement. I tell you why. Let me tell you in what sense it is. Yes, it's global statement. You take E and M supermanifold. In supermanifold, you have manifold. It is on the base of the underlying manifold. You take this manifold N, and on this underlying manifold, you can construct this manifold, and then you make symplectomorphism of this manifold. It is global statement, which 20 years I even knew how to prove it. Of course, now it's very difficult to repeat this proof, but yes, it is global statement. Now, very good questions. Now let's consider this example. I want to consider them as a manifold. Let's consider this example. First of all, here everything is very easy. First of all, let's consider arbitrary atlas of coordinates on M. Suppose X bar alpha is atlas of coordinates on M. It's very easy to prove using this atlas of coordinates. Okay, atlas, physicists say local coordinates, mathematicians say atlas, but it is the same. For example, there is a very beautiful theorem statement. Consider arbitrary volume form rho on M. Arbitrary volume form rho on M induces form rho square on Peter. Let me prove you this statement. It's a very beautiful statement. It's very important for us. It is here I play with this thing because you see, if you have, of course, any row on M on the atlas using induction, using changing coordinate, you can make unimodular. Every atlas, you can change it, the first coordinate, for example, here. You can make this atlas such that in the new atlas row will be equal 1. It is not so important, so difficult. What is much more important, let me define you what is PT star M. In PT on M, you have components xi alpha. Xi alpha. Now, let's consider. Now, let us.
I'm sorry. So M is
manifold. Classical manifold. Even.
What is xi alpha?
Xi alpha, it is atlas of coordinates. Chart. It's chart. I forget.
Alpha is an index for the chart. Atlas of charts and each atlas of chart.
Okay. Okay. Now let's consider forward. Let's consider, for example. If you consider, for example, this side, let's come. You have to consider momentum and change the parity of momentum. But I will do it. If you consider coordinates, for example, x side alpha, and consider here theta I alpha. Same. But if you go from the chart x side alpha, you go to the chart x side beta. You have theta I equals b theta I b x I. So using this rule, I can define change of coordinates. It is odd coordinates. Now I can define canonical bracket. To define canonical bracket, we define it by hand because I have this rule. We can define by hand that x r is a j in every map, in every chart equals delta ig. But this rule is very beautiful exercise, very easy exercise for students. This rule gives you that this is well defined. How you say it is in Russian. Correct, in Russian, correct, yes. Because in English we say well defined, yes. I forget. Okay. Okay. So now, but let's see what happened with the check. If you see this changing of coordinates, let us see what happens with the Berezinian transformation. xi prime equals xi prime of xx, and theta I prime equals theta I dxi prime dxi. If you see the Berezinian, look on Berezinian on this transformation, dxi prime theta t prime dx theta, because it will be squared. You see, because in Berezinian everything goes down, it will be dx prime dx determinant square. And this square says that you can define this square says you that every volume form rho on M defines volume form rho square on PTF. Very beautiful exercise. Now, you ask me,
What do you mean by rho square?
okay,
Well,
okay. Yeah. I can say it another way. Let's just, no, there is a no, rho square, yes, you're asking a good question. For example, let's consider unimodular atlas on X. Let's consider unimodular atlas on X. Unimodular atlas is atlas set the code of changing of coordinates Jacobian equals 1. If you have unimodular atlas on X, so all the forms will be coordinate volume form, and rho will be coordinate volume form. Rho will be equal to 1, rho will be equal to 1, rho square will be equal to 1, 2. So in this atlas, I consider, I define this. I define. Yes. Yes, because Berezinian is the square of Jacobian. I can define what? No. No, on this terrain, determinant. Oh, sorry. On this terrain, no. Determinant equal. The idea dx prime dx and dx prime dx. In this terrain, it will be determinant Berezinian will be equals 1. And here you will divide. The Berezinian, it is why we check parity. Changing parity is very important. Changing parity of here is very important. Now, let me answer on the question of yours. How we define rho square? No, we in some sense we define already rho square because we have atlas of coordinates. We have the atlas of coordinates xi alpha, and these coordinates. And in these coordinates, let me write the property of this atlas. I would like to say that the rho is a volume form. Rho is volume form on M, and you always can find an atlas such that rho becomes equals to 1. Rho becomes equal to coordinate volume form, yes, dx, coordinate volume form. So we see that.
No, they don't listen. So we are on the manifold. With coordinates, forget about
manifold M. Manifold M.
let's consider locally. So any volume form is some function, say A, dx1, dx2, and so on.
Okay.
Yeah, what is its square? Just write it down to understand.
Yes, yes, right. I just one second, I will write. One second, I will write. Just no, I choose the listen.
So what's the question? Just the square of the coefficient.
Yes, I wrote the atlas when rho equals to 1, and so if this atlas is rho square, it will be rho square. I wrote the atlas. Okay, I wrote the back exercise.
Forget about atlas.
I define you. My point is the following. Consider arbitrary atlas.
No, let's consider Rn.
Let's consider. My point is following that the map on the PT star M we will have rho square. No. If it will be 1,
M equals R1.
yes.
Volume form.
Yes, okay.
Volume form here is
Just with the square of the coefficient. Very simple. Square means square.
Then it will not be. What will be? And then
dx1 dθ coordinate volume form.
yes.
Yes, and this formula is well defined. Rho square dx theta, and this formula is well defined.
Yes, it is well defined.
Yes, it's okay. Now it's better.
Only when you think of it as a function.
Yes, no, it is well defined because on the change of coordinates it behaves in the same way. It's very important.
It changes by
Yes.
square or Jacobian.
Yes. Now, let me write the formula for the last one. Because you have here the functions. What is this function? If you have PTM. I just want to write you to see the divergence appear. If you have arbitrary function on x theta, for arbitrary atlas on n generates you Darboux coordinates on PT star n. Yes? So let's consider arbitrary function fx theta. Arbitrary function fx theta generates you polyvector field to the fx plus fi fix theta I and so on. So it's really polyvector field. It's easy to see that Laplace rho f, Laplace rho square f. It will be up to coefficient divergence rho for this polyvector field. Okay. So this example is, in this example, of course, it's very important. If you have, let's consider the case by rho when we atlas rho equals 1. If you take delta 0 on fi x theta I, fi x theta I, square dxi theta I. You see, I have chosen the atlas where all the coordinates for rho equals 1. In this atlas fi x theta I equals d of fi x dx. Okay, now it's okay. It's absolutely right. I just have chosen the atlas of coordinates where rho equals 1, and I did all the calculation in this atlas. So we see that this divergence corresponds to the You see, I took arbitrary volume form rho on M. Then I take rho square, and taking Laplacian with rho square, I came to this. Okay. Yes, and of course, M here is Lagrangian surface. Now, let me go to. Now, let me write you one because.
You have 25 minutes.
Oh, yes, okay. So the problem is because I have to introduce the second operator, which is the fourth operator. So we see that I wrote master equation. I wrote volume 4. We have volume 4. Let me write some statements which belongs to. Let's consider arbitrary. Let's write the definition. We say that rho is normal volume form, is normal volume form on P star M, because now on is the star. If okay, on arbitrary, if there exists double coordinates such that rho equals coordinate volume form to this double coordinate. Normal form is very important concept for me. Now, let me write this statement. Because
you can always do that.
sorry?
I'm sure you mentioned earlier that you can always do that.
No, I can always do on the manifold M, but on the odd symplectic manifold. On manifold M, I can always choose the rho such that rho is a new model. And using this base, I make a rho square. Okay, normal form. Okay, let me. No, it's okay. It's okay. Now, let me write this one statement. Consider let rho 0 be normal form on U. Let rho be another normal form. Then, of course, we see here that rho equals f square r0, f r0. Okay. This is a fact which I want to write you. Then I will explain. Then delta. It follows from this. That delta rho 0 of f equals this identity.
That is the Jacobian of the transformation between the two.
I will write it in a very simple way. Of course, because it's normal form rho 0, we can write here delta 0. Let me write you one identity which belongs to Batalin-Vilkovisky, and we call it Batalin-Vilkovisky identity. Let's consider delta 0 s square dxi dθ. It's also identity which many years I was Perezinian. Consider arbitrary double coordinates. If Batalin and Vilkovisky calculated it in 80s, it was the result which belongs to them. Long time I knew this identity, and so not a long time people knew this identity. And I never understood its meaning. Now I will give you the tool how to understand the meaning of this identity. And there are many statements. Second statement which I want to tell you that now I have no time. In the main equation, Batalin-Vilkovisky equation which I wrote in this way, we can write it. I have no time, but we can write it Hovhannes equation, very often people can write in the following way. And this way of writing, many people in string theory were fascinated by this in 90s, and it is one of the reasons why Hovhannes formalism was so famous, because very often equation of master equation you can write in this way. And honestly, now I will tell you the second reason what's the relation between these formulas. Now we define you the second operator. I defined you at the beginning of the talk the first second operator in a very simple way. Now we define you canonical operator. X prime and it is double theorem.
Any possible transformation on.
Yes, any of
yes, but they don't have to be normal form.
I will show you. Now, let me define you second operator. Let me define you second canonical operator, which I call delta. You see, operator which I defined before, it depends on volume 4. Now, I define operator delta on. You remember, I could set my talk would be about half density.
For half densities, yes.
Yes. Now I will define this operator. Suppose we have arbitrary half density, S6 theta, square root of BX theta. If x theta are double coordinates, then it equals the square x. And this gives you answer on all the questions we say. No, this is about this I will speak about, but it's not. No, it is operator. No, this formula that I gave you, it will explain many facts, including this formula. I will give you explanation. Just give you 1 second. Now I define you canonical operator on half densities. Why half densities are so important for me? I wanted to tell you one thing, it's very important. Before the beginning of this activity, much earlier, in 1985, with my friend, Ruben Makatsan, we did a work about finding integral invariants of odd bracket. We didn't know how to do that. And one invariant which we found, I have to now come to speak now about this operator. We came to half density. From very beginning, I realized that half densities have spatial role in Hovhannes geometry. Okay, so this operator, we have to prove it, but let me show how using this operator I will come to this identity. Okay. Yeah. For example, let's consider example when you have half density S, which is equal to 1 square root of dx. If you have half density which is equal to 1 square root of dx theta, plus S equals. Now, let us calculate this answer in arbitrary coordinates. We can do any coordinate. The same half density you can write in other coordinate. In other coordinate, it would be Berezinian. Dx theta, dx prime theta prime, dx prime. So we see that in other coordinates, it obeys the same rule. It's first. Second, Hovhannes master equation, which I wrote. In fact, it was a question not on the function. It was a question on the. I'm just translating. Sorry. So Hovhannes master equation, which I wrote here. It was a equation of densities. In fact, half density for people from quantum mechanics, wave function is half density. So, but for this question, you have to write in this way. And when you write half density, immediately this operator obeys to condition delta square equals 0. So you can define what you have densities, what's cohomology half densities. And the second question, which I want to, how much time I have to speak about differential forms and half densities.
You have 15 minutes.
Okay, in this case I have that. Now I will speak to you about how to make correspondence between half densities and differential forms. Because here I wrote about half densities, and half density corresponds to on every Lagrangian surface in EN. You can put differential forms. Let us I will write the formula which is a very beautiful formula. Suppose you have PTN. In PTN, N it is Lagrangian surface. It is N is Lagrangian surface. So this example is basic example. Let's consider arbitrary function, arbitrary differential form, omega I L dx I L dx on N. Now, every differential form defines a function omega x psi in PTN. On PTN, yes. Sorry. Yes, you are right. Now let me write to this function omega. I assign the following density. Let's take integral omega x psi. This formula belongs. Okay, I will tell you who belongs to this formula. This formula belongs to not to me, but very interesting. Theta. Square root. Let's show an example. This formula belongs to Schwarz, to Schwarz. In fact, in his paper Geometry of Hovhannes, he wrote everything. So the differential form corresponds to density. Let me show an example. Let me show just the same. Sure. No, it is exponent. Let's divide it is what operator. Let's try to operate. Statement, theorem, it's statement.
What is the statement?
No, it's statement because it has density. I said that statement, it will become statement when I will prove that it has density.
No. Well, we took a form omega on M.
Yes. To form omega, I assign something, and I say that this something is a density.
The statement is
yes.
What integral? Integration of the psi. Integration of the psi, d psi. Capital D psi, capital D.
Okay, let's show example. Let's consider example M equals MC, for example. You have dx1, dx2, dx3. So let's assign to dx1, I assign theta1, theta2, theta3, theta2, theta3, for root dx theta. For example, dx1, dx2, dx3, I assign half density 1 square root of dx. It's very easy to check. Yes, this formula will give you, but okay. It is what it is her watch operator here. It's written. In fact, okay. In the paper Schwarz, it was written everything except that it is half density. Okay, but it is long. It's long. Now, Now I have very little time. In this very little time, I want to say two things.
Just a moment. We had omega I
Yes.
1 and so on. Then you write omega x psi.
Yes.
And what is omega x psi?
Omega
Is it related to omega initial omega, or it is not related?
If you make expansion, it will be omega I on x psi I is 1/4 plus 2/4. Да.
Да, я понимаю.
Every time you see dxi, you write xi.
Yes, yes.
А это набор форм.
Да.
И мы такую как бы производящую функцию строим.
Каждый раз мы видим dxi, мы просто пишем xi. И тогда получаем функцию на вот этот четный.
Мы просто теорему.
Просто три обозначили.
Но все равно вот это пока не утверждено.
Сначала
И тут везде нельзя доказать, что
все. Это будет понятно. Значит, просто, значит, по дифференциальной форме построили функцию.
теорема, что это полуплод. Это легко проверить. Теперь давайте я сейчас сформулирую одну очень важную, очень красивую теорему. Давайте вернемся к тому оператору. Пусть ро произвольная форма. Ро произвольная форма. Only I have to speak English. Let rho be arbitrary volume form. Let such that vector of square equal zero. What can you speak? What can you tell about this? First,
So this is a condition on.
yes. Consider arbitrary volume form such that delta of square equals zero. Because from very beginning, you remember I told you that all the equation of Batalyon they were such. Now I will tell you that almost this it means that it is almost Batalyon for this case. First, I will find here a new concept. Vector of square. There is a formula which I have the time to write. It is equal sigma rho. To every volume form rho, you can assign, you can add by canonical operation of square root of rho and divide on square root of rho. And you return the function, sigma rho. It is a function which you have.
Yeah, you mean if rho satisfies mass equation? Yes.
No, arbitrary.
Arbitrary rho.
So the fact that delta rho square equals 0 means that this sigma rho equals constant.
Use that.
But
This one here, is this delta rho?
yes, it is the canonical operator. It's canonical operator delta. No, it's canonical operator delta, which I define on half density. You take canonical operator and apply it on half density. No, delta, canonical. No, my aim is to delta 0 at the beginning. At the end of my talk, I introduce operator on half density, which is canonical, and it does not care about delta. It's delta. And using canonical operator, I define half density goes to another half density. Divide on half density function. Now, so we see here all constant. We see because it is 0, it means that sigma rho equals mu. So we see that delta square root of mu. So we see here it possesses odd constant mu. Odd constant mu long time was under the case of benefit. In the case if this odd constant mu equals 0, you can go to Batalyon for this equation. Okay. Now, second thing that I have to say, what happens in Poisson geometry? In Poisson geometry, much more interesting things happen. The operator delta, which I introduced, it was of course canonical operator, but operator delta rho, which I introduced from very beginning, you can define for every Poisson geometry, for every odd Poisson geometry. You don't need And there you have Botany-Vilkovitsky groupoid, which I have no time now to speak about. But I want to tell you that from the beginning, the operator delta, which I wrote delta rho when I defined, it was BV rho df. This operator does not need symplectic structure, only Poisson structure itself. And we did with Ted Voronov, when I came to Manchester, we did very beautiful work about the properties of this operator delta rho, which unfortunately I have the time to speak you now, say now, but this operator delta rho square equals 0 again, and it has many interesting properties. Okay, maybe you will ask me questions and I will tell the answer. Yes, I finished.
Thank you very much. Questions, remarks are welcome. Katie, do you want to add something?
Sorry?
Yeah, you're welcome.
I just sorry, I didn't hear. There's a question, but I didn't hear it. That's a problem.
No, I asked you whether you can, whether you want to add something to Ovik's talk.
No, I think he said everything. Just
Okay. Okay, thank you. Any other remarks? Other questions? No remark, no question.
I can, if it's possible, to ask through Zoom.
Yeah, sure, you're welcome.
Okay. So if I understand correctly, so BV master equation, quantum master equation, looks like delta acting on semi-density equals 0, right? Canonical delta.
Yes.
And we know that this, from BV quantization point of view, this object on which delta acts is something like exponential of the action, right?
Yes, but you need half density, something which possesses half density. You need something.
Yes, and it is natural because another interpretation is that exponential of the action is a wave function, which somehow geometrically should be something like half density, right? Yes. But then my question is, what is the geometrical meaning of the action itself, which is like logarithm of
maybe I will tell you another thing. Maybe I will tell you that you have you have act by canonical operator on the exponent of the action, which is a function, but multiplied on volume form, on canonical volume form, which possesses every space of the fields possesses canonical square root of canonical volume form. So I agree with you. One of the way of the answer to your question is that action possesses. I would prefer to answer your question this way: that you have EIS square root of dx theta. So here you have you have here canonical semi-density, which is related with the basic ingredients of the space of fields and antifields. Yes. Okay.
It's very difficult because
okay. It is one of the way of answer your question, but I don't think that maybe. So you have action multiplied on the square root of canonical on spatial volume form. Okay.
Thanks.
More questions? More remarks? Well, thank you.
Okay, maybe I'll ask. Did you try to develop more this interpretation, this quantum mechanical interpretation? Because this quantum mechanically, quantum master equation means like quantum BRST operator acting on wave function equals 0. And delta operator is like quantization of it's a quantum BRST operator.
Yes, but what is it? What is it in quantum mechanics, in finite dimensional quantum mechanics? I don't know what is it. What is it simply? Because symplectic structure is on the space of functions. This, what you are telling me, I remember very well that I was thinking about these things. So my main problem was the following: I never could understand how to realize the space bracket in the space of the fields and anti-fields, how to realize in the quantum mechanics. Of course, the question that you ask is very interesting. I would be really very happy to answer. I don't know. Answer this question.
Yeah, there is, okay, it's a bit vague, but there is an interpretation that you take classical mechanics and then you, if I understand correctly, you add extra dimensions. So you turn it into a topological model where degrees of freedom live on the boundary. And in this topological model, this delta operator is like quantization of BRST operator of the mechanics, something like that. But okay, it doesn't make sense to discuss now. Maybe
I don't know. I don't know. It's really interesting. It will be. Sorry, what's your name? Can you tell me?
It's Maxim Ovik.
Максим, здравствуйте, Максим. Вы тут? Я не понял. Извините. Sorry. But anyway, it's very interesting question. But sorry.
Thank you, Eric.
Maxim is the organizer of your lecture.
Yes, but so more questions, more remarks. Then thank you very much. We meet time again here, and our guest will be Valentin Luchak. So you,
Тут реально будет.
yes,
Ой, как хорошо.
реально тут. Thank you for visiting the seminar, and goodbye. See you next Wednesday. Bye-bye.
Next Wednesday.